Hello everyone, welcome to the video lectures of nanoelectronics. Today I will explain about Kronig Penney model. Actually I will explain the concept through two parts and this is the part 1 of the session. So the Kronig Penney model is a simplified model for an electron in a one-dimensional periodic potential, and the possible states that an electron can occupy are determined by the Schrodinger wave equation, and the same concept and the same model is applicable to a superlattice also. So what is a superlattice? A superlattice is a MQW, multiple quantum wells, and there will be a smaller barrier thickness less than 5 nanometer, so that the neighbor wells are coupled or interacted to each other through the tunneling effect. So the band structure of superlattice can be revealed by applying the same old Kronig Penney model. Just check the potential well of superlattice. Consider V0 is the barrier height, and we also assume that the total energy capital E of the electron is less than the barrier height, that is V0. Also consider the well thickness small a and the barrier thickness be small b. And since the structure, the quantum well and the barrier is repeating because it is a superlattice, multiple quantum well, and the periodicity small d is equal to a plus b. Consider this point as 0. So towards right that will be a, that is the width of the well, and towards the left side there will be minus b, that is, since it is from considering from the 0 towards the left, it will be minus b. B is nothing but the width of the barrier. Now we can start the derivation. We know that the Schrodinger wave equation for one-dimensional particle is d square psi by dx square plus 2m divided by h cut square e minus v into psi is equal to 0. Here the psi is the wave function and m is the mass of electron, and h cut is nothing but h divided by 2 pi, and capital E is the energy and capital V is the potential energy. Here we need to consider two cases, that is particle in the well region as well as the particle in the barrier region. So first case, the particle in the well region, that is electron in the well region. So the particle can be anywhere between 0 and a. So here the potential energy will be 0. So the Schrodinger wave equation will become d square psi 1 divided by dx square plus 2me divided by h cut square into psi 1 is equal to 0, because the potential is 0. This can be taken as equation number 2. So the Schrodinger wave equation that can be taken as equation number 1. Now consider the case of the barrier region. So the electron can be anywhere between minus p and 0. So here the barrier potential will be V0, V is equal to V0. So the Schrodinger wave equation will become d square psi 2 divided by dx square plus 2m divided by h cut square into E minus V0 into psi 2 is equal to 0. And we also know that the energy is less than V0, so that we can rearrange the equation as d square psi 2 divided by dx square minus 2m divided by h cut square V0 minus E into psi 2 is equal to 0. This can be taken as equation number 3. Here the wave function is taken as psi 2. And psi 1 is considered for the wave function of electron in the well region. Here the wave function in the barrier region is considered as psi 2 here. And the wave number k0 is equal to square root of 2me divided by h cut square. So k0 square will be 2me divided by h cut square. So the equation number 2 can be rewritten as d square psi 1 divided by dx square plus k0 square into psi 1 is equal to 0. This can be taken as equation number 4. Now we can solve the differential equation. So this is the second order differential equation. The solution will be psi 1 is equal to a into e raised to first root into x plus b into e raised to second root into x. So how will you calculate the root? Root is equal to minus b plus or minus root of b square minus 4ac divided by 2a. So here a is 1 and b is not there, and c is k0 square. So the roots are plus or minus square root of minus 4 k0 square divided by 2, or plus or minus I k0. So the roots are plus I k naught and minus I k naught. So you can substitute that, and psi 1 is equal to a into e raised to I k naught x plus b into e raised to minus I k naught x. So that is the solution for psi 1, and this equation can be taken as 5, equation number 5. Now we can simplify the equation number 3. So equation number 3 can be rewritten as d square psi 2 divided by dx square minus q square into psi 2 is equal to 0, where q square is equal to 2m divided by h cut square into v naught minus capital E. So this equation can be taken as equation number 6. So solution to this equation, psi 2 is equal to a constant into e raised to first root into x plus another constant into e raised to second root into x. We have already taken a and b as constants. So here we can take as capital C and capital D as constants. By solving the equation 6, the psi 2 will become c into e raised to qx plus d into e raised to minus qx. First root is small q and second root minus q. This is equation number 7. Now the constants capital A, B, C and D can be obtained by applying the boundary conditions. Now we can check the boundary conditions. So first boundary condition is psi 1 is equal to psi 2 at x is equal to 0. That is equation number 8. The wave equations are same at x is equal to 0. Okay. Then if psi 1 is equal to psi 2 at x is equal to 0, the change in wave functions will also be same. That is d psi 1 divided by dx is equal to d psi 2 divided by dx at x is equal to 0. Okay. That is equation number 9. Since the wave functions are continuous, we can also written as psi 1 at x is equal to a will be equal to psi 2 at x is equal to minus b. This is the another boundary condition. That is equation number 10. So similarly, we can also consider the change in wave equations. D psi 1 divided by dx at x is equal to a will be equal to d psi 2 divided by dx when x is equal to minus b. This is the fourth boundary condition. That is equation number 11. Now we can apply the first two boundary conditions, that is equation 8 and equation number 9, to the equations 5 and 7. In the equation number 5, we know that the psi 1 is equal to a e raised to I k naught x plus b e raised to minus I k naught x. When x is equal to 0, that means e raised to 0, that is 1. So psi 1 is equal to a plus b. And in equation number 7, psi 2 is equal to c e raised to qx plus d e raised to minus qx. When x is equal to 0, psi 2 is equal to c plus d. According to the first boundary condition, psi 1 is equal to psi 2 at x is equal to 0. So we can written as a plus b equal to c plus d. That is equation number 12. Now the second boundary condition was d psi 1 by dx is equal to d psi 2 divided by dx at x is equal to 0. We know psi 1 and psi 2. Take the derivatives. D psi 1 divided by dx, that is d by dx of psi 1 was a e raised to I k naught x plus b e raised to minus I k naught x. Derivative will be I k naught can be taken as common. So I k naught into a e raised to I k naught x minus b into e raised to minus I k naught x. Similarly, for psi 2, that is d psi 2 by dx, that is d by dx of the wave function psi 2 was c e raised to qx plus d e raised to minus qx. Taking derivatives, here q is common. So q into c e raised to qx minus d into e raised to minus qx. So based on the second boundary condition, that is d by dx of psi 1 at x is equal to 0 will be equal to d by dx of psi 2 when x is equal to 0. When x is equal to 0, e raised to 0 term will be 1. So I k naught into a minus b will be equal to q into c minus d. That will be equation number 13. Now we can consider one theorem, that is Bloch's theorem. It states that the solution of our Schrodinger wave equation for a particle or an electron in a periodic potential will be the product of a function with a period of the lattice and plane wave equation, that is psi k of x plus d is equal to psi k of x into e raised to I k into d. Here d is a plus b, periodicity. Here also there will be multiple quantum wells and there will be periodicity. So the same Bloch's theorem is applicable to the superlattice also. By considering this fact, psi k of x plus a plus b will be equal to psi k of x into e raised to I k into a plus b. We can rearrange this equation as psi k of x is equal to psi k of x plus a plus b into e raised to minus I k into a plus b. This will be equation number 14. Here d is a plus b, that is a periodicity. In our case, consider x is equal to minus b. So equation number 14 can be written as psi k of minus b equal to psi k of a into e raised to minus I k into a plus b. Here the k is the wave number. Psi k of minus b, it is referring to the wave function in the barrier region. So psi k of minus b will be psi 2 of minus b. Similarly, psi k of a, that is referring to the well region, wave function in the well region. Psi k of a will be psi 1 of a. It can be written as psi 2 of minus b equal to psi 1 of a into e raised to minus I k into a plus b. This will be taken as equation number 15. From equation number 5 and 7, we can written as psi 1 is equal to a into e raised to I k naught x plus b into e raised to minus I k naught x. And from equation 7, psi 2 is equal to c into e raised to qx plus d into e raised to minus qx. And therefore, psi 1 at x is equal to a can be written as a into e raised to I k naught a plus b into e raised to minus I k naught a. And psi 2 at x is equal to minus b can be written as c e raised to minus qb plus d into e raised to qb. We need to calculate psi 1 and psi 2 at x is equal to a and x is equal to minus b respectively, because in equation number 15 there are two times psi 2 of minus b and psi 1 of a. So equation number 15 can be written as c into e raised to minus qb plus d into e raised to qb equal to a into e raised to I k naught a plus b into e raised to minus I k naught a into the common term e raised to I k a plus b. So this is equation number 16. So by considering the boundary conditions, equation number 15 can also be written as d psi 2 by dx at x is equal to minus b will be equal to d psi 1 by dx at x is equal to a into e raised to I k into a plus b. This is equation number 17. Now we need to calculate d psi 1 by dx and d psi 2 by dx at x is equal to a and minus b respectively. So d psi 2 by dx will be equal to q into, q will be common, q into c e raised to qx minus d into e raised to minus qx. When you differentiate, q will be common. Then d psi 2 by dx when x is equal to minus b, it will be equal to q into c e raised to minus qb, because x is equal to minus b, minus d into e raised to qb. Okay. Now d psi 1 by dx, it will be equal to, here the common term will be I k naught. So I k naught into a into e raised to I k naught x minus b into e raised to minus I k naught x. And when x is equal to a, d psi 1 by dx will be equal to I k naught into a e raised to I k naught a minus b into e raised to minus I k naught a. By substituting the values of d psi 1 by dx and d psi 2 by dx for x is equal to a and minus b in equation number 17, we can rewritten as q into c e raised to minus qb minus d into e raised to qb will be equal to RHS side I k naught into a e raised to I k naught a minus b into e raised to minus I k naught a into e raised to minus I k a plus b. This will be equation number 18. From equations 12, 13, 16 and 18 we can make one matrix form. So from equation number 12, a plus b is equal to c plus d, or a plus b minus c minus d is equal to 0. So when you write in the matrix form, the first row, that is a, that is 1, again 1, then minus c minus 1, minus d minus 1. Similarly from equations 13, 16 and 18 you can write the values with respect to the corresponding equations. So further solutions and discussion about the occurrence of allowed bands and forbidden bands and about the extended band diagrams of superlattice, that will be discussed in the second part. Okay.